I'm Scott Uhlrich, and today I will share with you how my colleagues at Stanford and I developed a muscle coordination retraining strategy that reduces knee contact force during walking. Reducing compressive loading in the knee is the target of many non-surgical interventions for knee osteoarthritis. Knee contact force reaches several times body weight during walking, and about one body weight of this force is the intersegmental force, or the resultant from inverse dynamics, while the remaining 50 to 75% of the force primarily comes from muscles. Kinematic gait modifications, like changing the foot progression angle shown here, aim to redistribute the intersegmental force from the medial to the lateral compartment of the knee. However, relatively few gait modifications aim to reduce the large muscle contribution to knee contact force. Previous simulation studies suggest that walking without activating the gastrocnemius muscle could reduce the second peak of knee contact force, but this hypothesis has not been tested experimentally. Today, I will show you how we taught individuals how to walk with a gastrocnemius avoidance coordination pattern. First, we used simulation to design a biofeedback strategy. Next, we tested that biofeedback experimentally. And finally, we used simulation to estimate the effect of the intervention on knee contact force. To design the biofeedback, we first asked the question of what muscle compensations would be necessary to walk without activating the gastrocnemius. We generated two static optimization simulations with identical kinematics but two different coordination patterns. The natural coordination pattern, shown with the solid line, had an objective function that minimized the sum of squared muscle activations, while the gastroc avoidance coordination pattern in the dashed line added an additional penalty to the objective function to further penalize gastroc activation. As expected, the gastroc avoidance case substantially reduced the second peak of knee contact force. At the muscle level, we saw a large reduction in gastroc force. To compensate at the ankle, soleus force increased, and to compensate at the knee, hamstrings force increased. But you'll notice that the increase in hamstrings force is less than the reduction in gastroc force, which is because the hamstrings have a larger knee flexion moment arm than the gastroc, which means they can generate the same moment with less force, which is why this intervention works. We used these results to design the biofeedback for the experiment. We wanted to teach people to reduce their gastroc activation, but retain a normal ankle plantar flexion moment, which meant that they would also need to increase soleus activation. We then moved to an experiment to answer the question of whether humans can change the activation of redundant muscles like the gastroc and soleus during walking. 10 healthy adults walked on an instrumented treadmill while we processed EMG from their gastroc and soleus in real time. They first performed a baseline trial where we measured their gastroc to soleus activation ratio during natural walking. We then gave them real-time biofeedback over 3 trials where their goal was to reduce the gastroc to soleus activation ratio, shown by the bar magnitude, as well as reduce their gastroc activation, indicated by the bar color. They finally performed a retention trial to see if they could retain the new coordination pattern without feedback. After the third feedback trial, individuals reduced their gastroc to soleus activation ratio by 24%, which was primarily driven by a 17% reduction in gastroc activation. And the same trend held true during the retention trial without feedback. Finally, we used simulation to see if the resulting gait pattern from the biofeedback reduced knee contact force. We used EMG-constrained static optimization with an objective function that minimized the sum of squared muscle activations and a constraint that the gastroc to soleus activation ratio in the simulation matched that we measured from EMG. And we observed a 12% reduction in the second peak of knee contact force, which is comparable to the effect of losing between 16 and 38% of body weight. In conclusion, we saw that humans can change the coordination of redundant muscles like the gastroc and soleus when we give them simple biofeedback. We then showed that a gastrocnemius avoidance coordination pattern reduces knee contact force and could be a promising intervention for knee osteoarthritis. More generally, this study demonstrates the utility of using simulation to design biofeedback that helps people learn more favorable movement patterns. Thank you for your time, and I look forward to further discussion.